Well, thank you very much for asking me to speak. I'll rattle on like I usually do. I'm not so used to being right up on a big stage like this. I usually suggest that if people want to interrupt me or yell out questions, feel free, but I probably won't hear, so it's probably better to take them at the end. 30 million jobs a year and counting is the title. I'll come back to that later. This is a bit of background about Imperial. We're one of the premier UK university research institutes. We're ranked number 2 with Cambridge University, MIT being the number 1. So I'm kind of proud of that. I didn't realise we were quite so high up the list until I looked this up. We're number 9 in the worldwide universities list from the Times Higher Education Supplement, and number 3 in Europe. 15,000 students, 6,000 of them are postgrads, so quite a high postgraduate percentage, and quite a lot of research staff. So there are as many staff as there are postgrad students. Between them, they add up to the same number as the undergraduate students. We're science-based. We just do science, engineering, technology and medicine. So we don't do any history or any literature, no high-performance computational French, for example. So that makes my job quite a lot easier, applying HPC only to science and technology and not the difficult things. We have quite a lot of industrial collaboration, which means that a lot of the research we do is quite practical and has a kind of engineering bias, which makes it easy for me to understand. £350 million a year income, that's like $700 million, give or take. Our main campus is in South Kensington. I was going to put a picture here, except it's a picture of a big tall tower and it looked really silly on the wide slide. We're actually on that site as a result of the legacy of the 1851 Great Exhibition. So whenever people talk to you about the legacy of some big event, here's the one example of something that I think is good that came out of it. There's us and the Natural History Museum, Science Museum, the Albert Hall, and the Victoria and Albert Museum, all on the site of the Great Exhibition. So the High Performance Computing Service, run a service for the entire university, £2 million annual budget. That's gone up from £1 million last time I was talking to you, so I'm twice as rich, which I'm really pleased about. And we also have additional income directly from research groups who choose to give us money to buy more computers for them to use, and that has an implication on our PBS configuration. We now have 5 dedicated HPC staff. They're very dedicated. I'm very proud of them. And it turns out we're the largest UK university HPC system in a recent survey we did amongst ourselves in the UK. That's because I haven't been throwing anything away. I've got loads of old shit running. So we have 3 systems. Imaginatively named, I thought, but our marketing people decided they want to rename our new computer, so we now have a competition going whether we should call it Gandalf or something. But CX1, which was our first one, a low-end cluster, mostly Ethernet, it's our biggest one. CX2, dedicated for really large MPI parallel jobs, and AX3 and 4, which are machines for genomics. So, running through that list backwards, AX3, 4, large memory SMP machines, SDI UV systems, lots of memory, not so many processors. They really just do next generation gene sequencing and gene assembly and stuff like that, where that kind of architecture is really good. Thanks to Alexis, who is here, we've got a really good configuration that copes with the topology and the CPU sets. That means that system schedules itself quite nicely. Round of applause if he's here. Really good job. Well done. That was too complicated for me to get my head around that problem, and he rescued me, so thank you very much. CX2, that's an SGI ICE system. It's basically just to run very large MPI parallel jobs, so stability and performance are the important things. From the scheduling point of view, it's just making sure you put all of the elements of the job on adjacent nodes. This is the one we're about to rename. If you want to join in the competition, I think anybody can. Go to the Imperial website. We're on the front page of the university website today. CX1 is the one that's more interesting, I think, for this group. It's a low-end cluster, mostly gigabit Ethernet. There are several InfiniBand islands as well. We're upgrading it all of the time. We're adding nodes basically when they're cheapest and best to buy, or if a research group has got some money, we'll go out and buy some nodes for them. Currently, 24,000 cores. Yeah, I was impressed by that. It goes up every time I count them. Nearly 1,500 nodes, 13 distinct hardware types, so 13 different Intel brand names of CPUs with different characteristics. So it's a bit tricky to schedule. Some of them have InfiniBand, some don't. Some of them have larger disks, some of them have larger memory, some of them have GPUs on them. So we use PBS Pro on all of those systems. But I was like saying, CX1 is the one that's the biggest challenge after Alexis had helped me out with the other one. So it's the largest system in terms of CPUs, so more CPUs, more cores to schedule. As you get bigger nodes, we've now got 20 cores per node, as opposed to the 4 we used to have. The core count is going up very significantly every year. A non-uniform topology, so it's not got one interconnect fabric, because that's too expensive. We've got lots of little bits that will need to be scheduled separately. Different node types, different sizes, so quite complex. And I want to make it as simple as possible for the users so that they don't have to submit to a particular queue, because in my experience, users always do that wrong. It's their favourite thing to do. I submitted it to the wrong queue. Why did you do that? Well, I just wanted to. So it's all done by automatic queue selection on the basis of the resources they specify on their PBS directives. So 80,000 jobs per day on average. Now, I only realised it was so many because I'd seen the PBS job number counter click round, and I went, oh, the first time we did that, we had a little party. That was like 7 years ago. And then I realised actually in that year it had clicked over 3 times already. So I went through, and we now have 30 million jobs a year. So most of the automatic selection is done doing route-only queues, except for the queues where the users actually own their nodes, which they're allowed to submit to directly. Seems fair enough. And I try to make it as simple as possible, so the users just need to specify the resources they need, such as the wall time, the number of nodes, and any special features like a GPU. So we don't assign nodes to queues. We found out we couldn't do that when we started using node grouping for the different layouts of the interconnects, which didn't map on one-to-one to the queues. We started using node grouping, and that's much more flexible. So we have a thing that looks like a queue, but it isn't, in fact, and all the other different resources related to the topology of the system and the interconnects can all interoperate with each other at the same time. And I think that might make the scheduler a bit busier than it has to be, because it has to think more. We run lots and lots and lots of serial jobs. The bioscientists really like doing serial runs, and they also like doing parameter studies. And we also have people who are processing images, and they like to, from microscope slides and things like that, and they like to do one image for each slide, one process, but then do it 20 times for each slide because they want to get the best result by changing the parameters. So a kind of exponential number of jobs. Quite a few single node parallel jobs, which is a really good sweet spot for a lot of ISV applications like Abacus and things like that. You get very good performance. And then slightly larger jobs running in parallel. And effectively, I split up those 3 categories just to make it a bit easier and to partition the work, so the single node parallel jobs go on the better nodes because they can benefit most from it, for example. So that's brilliant, fantastic. I'm so clever. PBS Pro has really made it so much easier for me to appear to be very clever and good at my job. Not that I'm not, of course, but But yeah, there's a few little cracks appear, and I thought it'd be interesting just to explore a couple of them. The faults, of course, are created by the users, because my perfect system is just lovely. So why isn't my job running? Well, because we use fair share and you're just too greedy. Okay? You've been put too much work in, you run too much, it's not fair on the other users. Or you haven't really thought about what you're doing and you've asked for like 1,000 hours of wall time, which is probably, by the time the job finishes, you'll be dead. So I'm not going to let you do that. but my job still isn't running. I can see other people's jobs running, and why not mine? It's not fair. Well, of course it is fair, because it's fair share, right? By definition, it has to be fair. But that doesn't stop them moaning, so what I've done is I've stopped them being able to see the other people's jobs. I think that's really clever. They can't complain about that, you know. They can think about something more important, like rocket science or whatever it is they do. But yeah, PBS guys, QStat, when you're looking at queues, gives away some information that some of my bright users can deduce stuff from. So I think we need an option to hide the queue configuration as well as the user's jobs. And it also, actually, people who've got their own nodes, if they've bought themselves on a private queue, it might actually be nice if they could see something on that queue on a per user basis. Okay, why is my job running? I'm an important person. I don't care about everybody else. I'm an important researcher, and my research is much more important than everybody else's. So this is where my perfect plans all get messed up, because, you know, they might be very important, they might be very rich, they might have a really good case, and I'm a bit of a sucker for a really good case. So one thing that comes in really useful with that is being able to have per user limits specifically for number of CPUs, number of cores, jobs running, all that kind of stuff. The extra flexibility that came in with that feature in PBS has made it much better for me to be able to manage exceptions, basically. And I think whatever system you set up when you've got a whole variety of different users, you have to be able to have some way of making exceptions, because that's just what life's like. But do remember, if you're setting special limits for somebody, take them off, otherwise they'll get too used to it. So another thing, making it so easy to use, and I think somebody alluded to this earlier, users submit much more work than they used to, and they're really tempted to run huge numbers of jobs. In the current version of PBS we're using, the server and the scheduler can kind of clog up a bit. And if we've got more than kind of 10 or 15,000 jobs on the system on occasion, it can turn to kind of sticky toffee. It works most of the time. We're normally running probably 1,200 jobs at a time, and we might have between 500 and 10,000 queued, and would expect to clear most of that 10,000 overnight, since the large number of jobs are the short ones. But yeah, if somebody does make a mistake, you can stop them by setting max jobs, which will stop them submitting any more jobs, but they've already got 5,000 there, and deleting those is really painful. On the user side, you give them a great facility. Sometimes they don't really check the answers. Or they go, well, I don't like the answers I saw, so I'm going to submit the run again. And it's not just one run, they submit 1,000. And they're thinking, well, why are you submitting the work again? Can the computer give a different answer? Well, you know, with computer maths, I suppose theoretically it could, but I don't think you're quite advanced on that level of computer mathematics. So what I really do notice a lot is that if you put a scientist in front of a computer, suddenly the scientific part of him evaporates and goes away into the cloud or something. And they do things that like, well, you know, I submitted it once and it failed, so I submitted it again and it failed again. Yeah, well, what did you expect? But on a more subtle level, they seem to think that the computer's always going to do the right thing. And it's not always going to do the right thing, it's just a computer, it does what you tell it. So what I'm beginning to see is not very careful checking of results. Because they can submit so many jobs, it's quite onerous for them to check all the results and to look at all the listings and check for error messages. Now, for a real experiment, you'd be careful, but for computer experiments and simulations, they seem to be less keen to do that rigorously. And I think creating tools to check the outputs and the data files from the runs is a really important area, and that's something that people should do more often. So they run it the third time and still it doesn't work. But something that's more interesting is that they might have thought it's worked, and they've got results that on the surface look like they might be okay, but actually the contents of the results is not good. and they really need to do something more advanced and validate the output data. Now, the people in the rocket science are probably more aware of that. People in materials and things like that might not be, because it's all completely theoretical and they don't have much of an experimental basis. And certainly the bioscientists are used to a world which is constantly changing, and often they don't really think about that until they find something that doesn't fit with their mindset, even though it might still be wrong. So I think the computational science now needs to push back a bit, and the people who are using HPC need to incorporate it better into their science and to link the two together more closely so that they can support each other in a stronger way, rather than just going, oh, well, I ran the simulation, it was fine, it proved what I thought. So a little bit about PBS Pro. So we are beginning to see some bottlenecks. We're not on the latest version of PBS Pro yet. We're going to upgrade soon. And I hear there are some performance improvements. But I think that's going to be a continuing driver for the development. As the number of cores increase, I've got twice my budget. I started out with 2,000 cores 8 years ago, and now I've got 24,000. So if we extrapolate, I'm going to have 100,000 cores in 5 years' time, and the big guys are going to have hundreds of thousands, if not millions. And on top of that, I'd like to make more complex scheduling decisions within my configuration. So I'd like to have ands and ors and compound expressions and things which will make the time taken to work out which jobs to schedule much harder for the scheduler. And I'd also like to be able to look inside the select directive in terms of when I'm scheduling jobs, rather than just the global resources for the job. I want to see some of the details inside the select, because that's important to some of our users. Please. That was it. Now, nobody asked any questions during the talk, so I guess there aren't any.
First, thank you. Then before I open it up, you need to go back one slide and you need to tell me what you mean by I want more control inside the select directive.
So you can put -L select equals 1 n CPUs equals 12 to say I want a node with 12 CPUs. Now, I know what kind of hardware supports that in an optimum way. So I can put it onto one of my queues where all that stuff gets set correctly. But I can't get that number 12 out of there. All I get is the total number of CPUs for the job. So if I've got select equals 2 n CPUs equals 12, I've got 24. Now, is that one 24 CPU node or two 12 CPU nodes?
That was my question, anyway.
Or if I've got a special flag on a node, like we have a thing for temporary scratch space or GPU types and things like that, they all get stuck on as part of the node attributes. Sometimes you'd like to be able to say, oh, that's not going to work because I know there aren't any kinds of those GPU nodes on that queue.
You really should be talking directly to Alexis, who's going to take care of this for you.
I know Alexis can do just about everything, anything.
Excellent. Okay, sorry. Any questions for Simon from the audience?
I think I heard you say you had up to 12,000 jobs or something running at one time, and
yeah, probably more than 1,000 jobs running at any particular moment.
do you have any kind of tools to see what those are doing, some kind of a dashboard or anything that you've developed as far as memory footprint, I/O, those kinds of things?
So we use the accounting stats to get historical information about job sizes and shapes. Actually being able to look at what's running at any one time with such a diverse workload, I don't think is actually terribly useful for us, because it's too big a thing to look at just at once. If you've got 1,000 jobs running, some are chemistry, some are physics, some are biology, is that useful information? The thing that is useful is being able to pick up nodes that are different in some way. So we're using things like Nagios and other monitoring tools to pick up high system time or I/O wait time or a memory shortage, and that usually is a result of a user error of some sort. So it's useful to get that kind of information.
So does Nagios scale to that many CPU or that many hosts?
Nagios.
Yeah,
No.
does it? So what do you use to actually look at that level?
So we would normally, so Nagios, we've got to set to quite a low polling interval. So it will flag up, there's probably like 50 nodes in some strange condition at any one time. And we might choose to actually log into those nodes, SSH to them, and actually manually see what's going on.
Okay.
It would be kind of neat to be able to have a dashboard that had all of the nodes as PBS knows them, and being able to pick up the parameters, certain parameters to display for groups of nodes, because if they're parallel jobs, you can immediately see which job it is that's being a bit funny as a kind of user diagnostic tool. But we don't have that right now.
Okay.
On our ICE, we've got PCP, which works a bit better.
Do you have any like I/O bottlenecks, and how do you schedule and limit the number, how much I/O can be on a node, if you do that?
We do have some. I have to say I think we're probably quite lucky in that I/O boundedness is generally not much of a problem for us. The biggest culprits are the bioscientists, who tend to move lots of data around, and whenever they buy nodes they always want them with 5 terabytes of scratch space on them. So the usual thing is a user will submit 1,000 jobs, each using a file which is 3.5 terabytes in size, and we'll copy it to the local disk on the node because that's good, we tell them to do that. But then you get like 100 copies of terabyte sized files all happening at the same time, and of course the file server it comes off doesn't scale to that level. So I suggested to one user maybe he'd just put a little delay, a random delay in each of his jobs if you're going to submit a lot of them, just to kind of spread it out a bit. And he did that, and it was random, but it was random between 100 and 110 seconds because he hadn't calculated his randomness properly. So it was great.
Any other questions? All right, thank you again.
Thank you very much.